In this next segment, we're going to look at the relationship between the mean squared error and the model that we've been working on. So we're going to try to minimize the mean squared error for this very simple model in our TOEIC problem that we've been working on, which is the constant model, right? So we have our TOEIC data set, and we saw that the value of the parameter that minimizes the mean squared error was 25. This happens to be the mean of our observations. So what we're going to do in the next couple of sections is find two different complementary ways of looking at why the mean is actually this value that minimizes the mean squared error. We're going to do it first by doing a standard sort of calculus derivation that should be familiar for you all from a Calc 1 course. And then we're going to do a derivation that basically doesn't really rely on calculus, even though at the very end you could argue that we're sort of bypassing calculus, but that relies on certain algebraic tricks that are actually quite common in these kinds of statistical manipulations, and that it's useful for you to become familiar with. So the slides have all the algebraic details. I find it very hard to read mathematics on slides if somebody just flashes equations at me. So what we're going to do is we'll try to do a derivation kind of board style. Since my handwriting is not all that great, you can refer back to the slides for the cleaner rendering of the equations, but hopefully seeing the material kind of come alive in handwriting will make it a little bit easier. I encourage you to do these derivations yourselves. They are very straightforward algebraic and simple calculus manipulations, but you should be comfortable with them. So this is the section of the slides that I'm basically going to skip now and switch over to the iPad. So let's now look at the quantity that we're trying to minimize, right? So we are looking at our empirical risk, or mean squared error, average mean squared error, which is 1 over n times the sum of y sub I minus theta squared, right? And we want to know what is the value of theta hat, that minimizes r theta, right? This is our question. So we're going to answer that by using a little bit of calculus first. Next, we'll see this done with algebra, as we said. But we want to ask, where is this derivative of this function as a function of theta equal to 0, right? As you remember from Calc 1, when we have functions of a single variable, we can find a necessary, though not sufficient condition. We'll revisit that condition, a necessary condition for minimizing it, to be that its derivative at the minimizing value vanishes. So what is that derivative? So the derivative of r theta with respect to theta is equal to, well, this is the derivative of a constant. The derivative goes through. The derivative of a sum is the sum of the derivatives. And finally, we have to take the derivative of this square. So we have a 2 times y sub I minus theta to 1 less power, to the power 1, times the derivative of the inner function, right, by the chain rule. And the derivative of y sub I minus theta as a function of theta, the derivative with respect to theta, is equal to minus 1, right? So this derivative right here is equal to, we can kind of condense these terms. We take the 2 out, we take the minus 1 out, right? And we end up with minus 2 over n times the sum from 1 to n of y sub I minus theta. And now we want to ask, how can we make that be equal to 0? Well, the minus 2 over n doesn't matter, all right, because it's a multiplicative constant that can't be 0. This whole term is the product of two things, minus 2 over n times the sum. And for the product of two quantities to be equal to 0, at least one of them has to be 0. The minus 2 over n can't be 0 for any finite value of n. So we're left with asking, when can this sum be 0? And so we can ask, when is that sum 0? We can find that out by breaking up the sum into its two component terms. This is equal to the sum over I of y sub I minus the sum over I of the value theta, and we want that to be equal to 0. But this sum is equal to what? Well, we have theta, which is a constant. It doesn't depend on I, so we're summing theta multiple times the same thing. So in how many times? Well, this is a sum for I running from 1 to n, which means that in here we have a total of n times the value theta. So in summary, what we have is that the sum of y sub I minus n times theta has to be equal to 0. And we're looking for the special value of theta, which we'll call theta hat, right, where this happens. And from here we can see by moving this to the right that n theta is equal to y, or, and I'm just going to flip it for notational convenience, that theta, the special value of theta where this happens, is equal to 1 over n times the sum for I from 1 to n of the y sub i's. Okay. So this special value where that derivative vanishes is equal to, or rather, maybe let's not call it theta hat quite yet. Whoops. Didn't mean to erase all that. Let's not call it theta hat quite yet. Let's say that this particular value of theta, where this happens, let's say theta star, is equal to this, which is by definition the mean of y, which we also write as y bar, right? That is the definition of the mean that you all know and love. The question is this value the minimizer? Does the function truly reach its minimum there? So the question we need to answer before we're done is theta star where r of theta is minimized? Right? That's the question before we declare victory that we need to answer. And remember that for functions of one variable, we can have a couple of different situations. We can have, if this is r of theta, right, the derivative as a function of theta, if this is theta, here at a minimum the derivative is equal to 0. But the derivative is also 0 if r looks like this. And it's also 0 if r looks like this, here obviously, right, as a function of theta. And it's also 0 if r looks like this. Right? All these three cases have 0 derivatives. This is a minimum, which we're looking for. This is a maximum. And this is a saddle point. All these three are critical points where the derivative vanishes, but in order to find out whether the point we found is actually a minimum and not a maximum or a saddle point, we need to find out what is the shape of the neighborhood of the function. Does it look like this? And look like this means that the second derivative of the function with respect to theta should be 0, because in this case, the second derivative is negative, and in this case, it's equal to 0, right? So we're looking for whether that derivative is greater than 0. If it is, we're good to go. If it isn't, then we didn't find a minimum. So now what we want to ask is, what is the second derivative of r of theta with respect to theta equal to? So we need to go back to our derivative. This is where we found the value of the derivative. We had found it right here. So now we're going to take the derivative of this quantity. So we want to take the derivative of, with respect to theta, of minus 2 over n times the sum over y of y sub I minus theta. And this is going to be equal to minus 2 over n times the derivative of the sum, which is the sum of the derivatives. And the derivative of this quantity with respect to theta is just minus 1. The derivative of y sub I minus theta with respect to theta is just minus 1. And so this is a sum from 1 to n, so its value is equal to minus n. And so we have that this second derivative is equal to minus 2 divided by n times minus n. The n's cancel, 2's cancel, and we have found that the second derivative of r with respect to theta is equal to 2, which is just the number 2, most certainly greater than 0. So we did find that indeed the mean is not only this value, it actually is, now we can call it, it is actually theta hat, the value where the mean squared error is minimized for the constant model. If your loss function is the squared loss, then the optimum value is the mean of the data. It is the best you can do under the condition where you're asking, I want my model to make the least possible squared total error, squared average error. Then the best you can do is pick as the number that will describe your data, pick the mean of the data. That's the best you can do, and this is shown by calculus. Now, in the next section, we're going to look at this exact same question from an algebraic perspective, not just for the sake of doing algebra, but because it actually enlightens us and it shows us something about the structure of this quantity.